Okay, so I wanted to do a couple problems that we would have done on Friday. Uh, this problem in here, the uniform 4 kilogram cylinders, each has a radius of 150 millimeters. So what I would do is take a moment to pause and write out what you think this should look like in terms of each disk, because as we've seen in other problems like this, where we have two disks, we usually treat them individually. That way, we're able to set up a couple of sets of equations and then solve. So, in essence, the disk A is moving at 50 radians per second by itself, and then it's brought into contact with disk B. After disk A rotates a total of three full rotations, disk B rotates one full rotation. At that point, the two disks are rotating at the same rate, so slipping is no longer occurring. So the only force really that's at play here is the friction force, which is creating a moment about A and about B. So that's how we're going to treat that. So this is again a simple energy problem. And so let's go ahead and set it up. So I would say try as much as you can, and if you can't, then look at what I've done. Okay, so here's what we have. You can see that on the top we have disk A. So there's a reaction AX, the weight, the friction force. Friction force, of course, is opposite the direction since it's being driven down that way, and the normal force. Okay. And then the bottom disk, we have the friction force going the opposite direction, the normal force, and Bx and By. So there's a By here because versus A, which was in a open shaft or an open collar, so it's free to move up and down, whereas B was not. And then, of course, it's going to have an X reaction. So with that, what information do we have? Camera's not behaving. So with that, what do we have? A rotates 3 revolutions. That's our 6 pi. That's our distance. B rotates 1 revolution or 2 pi. That's our distance. And that's before we know that omega A equals omega B. So after this happens, both are moving at the same rate. All right. So we know both disks are the same size. They both have the same moment of inertia, 1/2 mr squared. So that gives us 0.04. So we'll start with cylinder A. Now, we start with cylinder A, and what I'm going to do is instead of drawing this for you, because the focus is not so good, I'm going to go ahead and walk through this. And I would say the more you can do this on your own, the better off you're going to be. So I would see what you can do with cylinder A before you look at my work and then go through. Now, cylinder A. So we're going to say some of the forces in the Y are zero. So we know normal force minus W equals zero. Therefore, normal is 4 times 9.81 or 39.2 newtons. We know the maximum friction force is going to be mu K times the normal force or mu K times 39.92. Now, as I said, this is an energy problem with our m theta. So our m theta is essentially going to consist of the friction force times the radius to create a moment times the number of rotations. We're going to have a T1 plus U1 to 2 equals T2. So in the first case, we have the kinetic energy of disk A moving. It's going to lose energy based on the friction force, ma times theta, and that's going to give us our 1/2 IA omega final. And I'm labeling that omega final because we know both omega final for A and B are the same, so we can just leave that as F versus saying omega A final. So if I plug in my numbers, I get something like this. 1/2 0.045 for my moment of inertia times 50 squared minus mu k times 39.2 times 0.15. That's my moment right there, right? The friction force times the distance times times the radius gives moment times the total distance is 6 pi. So if I look at the units, we can see kilogram meter squared times radian squared per second squared. Again, radians don't count, so it's just kilogram meter squared per second squared. Same thing here. You have kilogram meter second squared for this, and then the additional meter gives meter squared. So the units are consistent all the way through. And then on the other side, we know that's just going to equal to 1/2 IA final, which is just half of the moment of inertia gives us that. Okay. So we end up with one equation, 56.25, which is what this is, minus 110.8 mu k equals that. So that's our first equation. So we're going to do the same thing with cylinder B. With cylinder B, uh, it's the same idea. The only difference is, again, T1 plus U1 to 2 is T2, but cylinder B has no T1. It's not moving, so it's 0. So really all of the energy put in by the friction is going to be what results in the final omega. So in that case, we have the same idea. It's still mu kinetic times 39.2, since the normal force is the same, times the radius 0.15. Only in this case, we're only going around 2 pi versus 6 pi in the previous one. That's going to equal 1/2 0.045 omega final. We end up with 36.98 mu k equals that. So that's our second equation. So we have one equation, two equations, two unknowns. We solve. We get a friction coefficient of about 0.38 and a mega final of 25, which is coincidentally half of the original. And that's only coincidental. You couldn't have predicted that. Okay. So that's how you do that problem. So I know I went through it quick, but my hope is that you're just going to look at this as you struggle through, and not struggle, maybe just work through it and understand it. So we have one more that we would have done on Friday, and then I'm going to continue on tomorrow, so that should be all caught up. Okay, so let's look at another problem. This one here. And we're looking at this one here, this energy problem. Now, I like this one because it encompasses a couple of things with energy. So if we think about what we're doing, we have a uh, pulley, double pulley. We're given the information about it. We're given that the B is 15. We're given A is 5. Uh, there's a force P being pushed down on A, and it goes down a total meter. So we know we have force times the distance. We have gravity pulling A down. But since the system starts at rest, the only really energy into the system is that P pushing down and the gravity of A. The rest of it has to go, all that energy that's created there has to go to spinning this disc and pulling this 15 kilogram up a frictioned incline at 30 degrees, where the friction coefficient is 0.2 kinetic. So we want to know is how fast is A going when it hits the ground after falling 1 meter, and how far up does B go? Now, from the ratio of the pulleys, we know that B is going to go some distance of A, and it turns out to be 0.6 meters. So for 1 meter of A, it's 0.6 meters of B. But once A hits, B is still moving, so it's not going to stop instantly. It's going to keep sliding. So we're going to look at it as velocity here, and then we know this will move 0.6, and then what's the total distance? So again, if you just follow through what I say without really pausing and trying it on your own, you're not going to get much out of this. So I would encourage you to pause, write out the problem, do as much as you can, and then only use my notes as needed. Okay. All right. So we start with this. So here is our diagram. Now we have, as I said, the radius is 0.25. 0.15 for B. So, and then here's the information. P is 200. Mu kinetic I turns out to be 0.384 of the disk because you're given the radius of gyration. So we want to find velocity at impact and the distance B slides up total. So we know this relationship, velocity of A has to be equal to omega C times RA. Velocity of B has to be omega C RB. So knowing omega C is the same, and if we plug in RA and RB, we get a ratio of 0.15 over 0.25, or essentially that's going to be zero point 0.6. So what that means is that the velocity of B will be zero point 0.6 of whatever velocity A is. It also means that the distance A moves, which is given as 1 meter, is going to create to an initial movement of B of zero point 0.6. Okay. So let's first look at the velocity. So velocity impact. So we know it starts at rest. So T1 is 0. And we're going to use T1 plus U1 to 2 equals T2. Or again, U1 to 2 is going to encompass everything. So what do we have for U1 to 2? We have the force P times the distance, we'll call SA, which is 1 meter, plus the mgh of A. And then opposing that is going to be the friction force of B times the distance it slides. And then also it's going to be the increase in gravitational potential energy of B as it goes up an incline. All right. Now to get there, we first need to figure out back to statics, right? We know that if we sum the forces in the y, where we make our incline like that, we can then determine our normal force is going to be mg cosine theta. That gives us 15 times gravity times the square root of 3 over 2, which is the same as cosine 30. It gives us a normal force of 127.4, or a friction force of 0.2 times 127.4, or 25.5. So that's our friction force. And then the other thing we know is that's just the friction force. And our MGH is going to be the mass times gravity times the distance, 0.3. And we know that earlier we figured that in this first part, this is again when the velocity hits the ground, this B is going to have moved 0 0.6 meters. So that means because of a 30-degree angle, this is going to risen 0.3 meters. So we have that much. We have 44.14 Newton meters there. And for the friction force, we have 25.5, and that's going to be times 0.6 also. So what we end up with is our U1 to 2 is what? It's going to be the force 200 times 1 meter plus mgh of A minus the friction force times the distance it slides, 0.6, minus the mgh of block B, which is here. So we end up with a total of 189.6 joules. That's how much excess energy we have that can be converted to kinetic energy. With that, we look at T2. So T2 is going to be what? We have the kinetic energy of A, the kinetic energy of B, the kinetic energy of the disk. So we want A, so we can substitute. We know it's going to be 1/2 mass times VA squared plus 1/2 15, but we know that VB is 0.6 of VA as shown earlier, so we substitute that there. And then we also know that 1/2 I omega, where we know that V equals omega R, or omega equals V over R. So I just pulled out the radius 1 over 0.25 squared and then the VA squared. So to isolate A. So now I know that my T2 is just equal to 8.272 times VA squared. And voila. So, and again, this is the quick version, but you should be working this through on your own. So now we get T1, right, which was 0, plus U1 to 2 equals T2. And so 0 plus our 189.6 joules, which equals 8.272 VA squared. We're able to solve for VA and get 4.78 meters per second at impact. Now that corresponds to an omega of 19.5, right? Because omega is VA divided by RA. So that would be VA divided by what? A quarter, which is the same as multiplying it by 4. So we get 19.15. And then VB, again, is 0.6 of VA, so it's 2.873. So now the question is, how much farther did C go? So we established the impact velocity, but we still have kinetic energy of both VB and omega C. So the question is how much farther to go? Well, 0.6 meters plus how far? Well, for this, we're going to say T3 plus U3 to 4 equals T4. Now, T4 is when ultimately everything stops. So what's that going to be? Well, T3, of course, is the kinetic energy of B and I of C. So we know that's going to be 1 half 15 times 2.873 plus 1 half I times that squared. So that's how much energy is at impact is available, 132.3 joules. Okay. And then we have to get to the very final part, and that's this. So we know that U3 to 4 is going to be what? It's going to be the friction force, which we know to be 25.5 times the distance. That's what we're solving for. And then how far is the MGH? Well, we know it's going to be 15 times the mg, and the height, of course, is this, sine 30 times that. So we plug all that in, we solve for SB, we get minus 99.06 SB. Okay. And that's pretty much at the end now because we know that's going to be roughly 132.3 joules minus 99.06 SB prime equals 0. Therefore, SB prime gives us a value of about 1.336 meters. And then if we add SB, the original 0.6 to that, we get 1.936 meters. So that's the total distance slides. Okay. So again, you should be able to go through this on your own, use my notes if needed, but this is a good example of how energy is used in rigid bodies. Notice the only big difference is now we have to deal with I omega squared, okay? And moment times theta like we showed before. All right, thank you.